Great, thanks. And our goal is to go no longer than 1 hour, I think, right?
Yeah.
Okay, great. Yeah. Well, thanks so much. Yeah, I'm Rob MacCurdy. I'm an assistant professor in mechanical engineering with courtesy appointments in computer science and also in ECEE. The stuff that I'll show you today, I think, as you'll see, is really interdisciplinary, and so it's why I was interested in having a presence in those different departments and interacting with students in those different departments. First, I want to say thanks for joining me today to hear about the work. I am really happy to take questions at any time. I'd rather that this be more interactive than me just kind of blabbing for an hour. And so please jump in with any questions as you have them. I'll try to remember to pause for questions also, but sometimes I get carried away. So if I don't, please do just jump in and ask me questions. Yeah, videos on are great. It helps me to assess what folks might be thinking about. Zoom is such an isolating means of trying to interact with people. I felt like it was back to 2020 today because I have COVID, and so I've been teaching from home, and it's an isolating experience. So the videos make it a little bit better. So I think what I'd like to do is to share the two major flavors or themes of research that are going on in the lab. And I'll start off with a project that that I currently have funding for right now and have a very urgent need to find some folks who are interested in working on. And then I'll also talk about some of the other work that we do in the lab, not to try to give priority to one versus another, because they're all important and interesting areas to work in. But the one that I'll show first is one that I'm recruiting for like this week. So I thought I'd start with that, and then I'll switch to a different one. So let's see, share my screen. Here we go. Okay, great. Okay, so let me try to make your views a little bit bigger. Cool. All right. So this is a theme that I developed some years ago, and the basic idea is to try to develop tools and technologies that will aid conservation biologists, ecologists, scientists in the study of animals in the wild. Historically, not to malign the whole discipline too much, but historically, the discipline of studying animal behavior has been really heavily weighted toward field personnel and time in the field, and less so toward technology development to try to leverage their efforts and really extend their efforts. And so what I'm going to tell you about today is some efforts in radio frequency tracking. So this started many years ago when I was between my undergrad and grad programs working as an engineer at the Cornell Lab of Ornithology, developing a whole bunch of different kinds of tools and techniques to monitor animals. And so you can see I've got some this is actually an acoustic receiver that I put out in Texas, and this is an acoustic receiver that I put out in a forest in Ghana. This is an acoustic receiver that is still in use in oceans around the world. This is actually a vibration energy harvester for a hawk moth. This is a little acceleration logger for a hawk moth. So lots of things there, and that remains the sort of broad area of interest remains a theme, but in particular, what I want to tell you about today is radio frequency tracking. So the real motivator here is that birds are really, really tiny. And so this plot shows you the distribution of body masses of all extant, meaning still alive species of flying vertebrates. So both birds and bats. And there's a log scale on the x-axis. And the way to read this is that, you can see if you're, say, in this area, that means that, sorry, is my audio chopping up or is it okay for you all? It's good. Okay, good. Let me see if there's anything that I can close here just to help in case. I can close that. Okay. Okay, so back to the plot. So when we are right around here, you can see that we're right around a body mass of between 10 and 25 grams. And so what that says is that most living bird and bat species have body masses that are between 10 and 25 grams. All right, fine. combine that with another piece of information. And that piece of information is that if you want to put something on a bird or a bat, that bird or bat can carry only between, call it 2 and 6% of its body mass in added payload. Otherwise, it's just carrying too much stuff. So if we use that heuristic and we then combine those together, you get these curves, which sort of look like a CDF. And the way to read these curves is, if you want to be able to apply the same tag to a certain percentage of all of these species. So for example, this horizontal line here corresponds to 50% of all species. Well, you move this line over to one of these CDFs and then down. So if we're at the 3% loading heuristic, which is a very common one, then you wind up with a tag mass that has to be 850 milligrams or less. All right. And so the idea of this plot is to try to allow people to kind of trade things off. So if you are happy making it such that most species are too small to carry a tag. So if we're up here, for example, meaning that only 20% of extant species would be capable of carrying a tag, then you come over to about here and you go down and you'd find that the tag mass was maybe 8 grams or something like that. So it's a heck of a lot easier to build an 8-gram tag than it is to build a 0.8-gram tag. And that comes down to really battery mass. All the electronics are getting smaller every day, but battery density has not increased at the same rate that transistor density has increased. Okay, so it's really all about power. So what I'm going to show you is an attempt to make a tracking system that is very miserly with its power consumption. For some background, here are examples of existing tags or transmitters that are out in the world that come from other sources, including commercially available sources. And they can be legitimately tiny, which is remarkable. You know, here's one that's on a dragonfly. Here's one relative to a dime. The upshot, though, is that these things don't last very long because they're all battery for the most part. All right. And so it's all about, here's the key nugget, is that basically it's all about how you use the battery in terms of the tag lifetime. The other caveat, like I said at the very beginning of this, is that we would like these systems to be automated. This guy holding this receiver and this directional antenna is in the process of trying to localize one of these style tags, a kind of old style tag. And so for a person to localize a tag, you have to go out and point at the tag by determining what's the direction of the strongest signal, move somewhere else, point again at the tag, and then sort of cross those two bearings to roughly estimate where the tag is. So it's very labor intensive. GPS is certainly a possibility, but it's not really a viable possibility because it's not very good in terms of its power consumption. And I can talk a lot more about that, but it's about, as I'll show you, it's about 1,000 times more energy intensive per position fix than the solution I'm going to show you here. All right. And by the way, just to kind of show you how GPS and these other existing small tags fit together in terms of their mass, you can today buy a GPS that is as small, a GPS tag for birds or other animals that's as small as about 2.5 grams and, up from there. And then you can buy these little tiny tags that I showed you on the previous page, which are compatible with this guy out there in the field pointing this directional antenna. Those tags can be bought with masses as low as about 1/4 of a gram and up. But they have the limitations I just discussed. So GPS, great, gives you lots of positions, but it's too big. And the other tag, although small, is not automated. So that's the gap that we're trying to fill with this. Let me pause and see if there are any questions. Let's see, I think I saw a chat entry, but it's hard to see that. Okay, oh, that was just Rushdie. Okay. Any questions for anybody in terms of the motivation? Okay, we'll carry on then. So this is the takeaway. When you can build a system, as I'll show you, you can wind up with a system that is really, really low mass. So on this plot, to be good, you want to be way to the left and way up toward the top. So things that are increasingly up here in this direction are increasingly good in terms of long-lived, very lightweight animal tagging technology. So the thing I'll show you today is the unique entry in this plot that's way the heck up there at the top. I'm happy to go back to this plot and tell you more about it. There's a lot more in there, but suffice to say, for this application, I think this is the right way to do things based on this comparison set. So how does it work? This is the original version of the system. And by the way, why am I pitching you this? Because we're building another version of this. This original version was fun to work on, but I'm the only person who can make it run. It's not scalable. The mission now is to disseminate this technology out into the world. So we're trying to rebuild the system with commercial off-the-shelf technology so that it can be scaled and really, really low cost. So there's some challenges there. Okay, how's the system work? It's basically like GPS in reverse. And so I called it an inverse GPS system back in the day when I wrote papers about it. So the way that it works is that a transmitter sends out a signal, and then a network of nearby receivers, nearby meaning up to 5 or 10 kilometers away. So nearby terrestrial receivers receive that signal and then very precisely measure the arrival time of that signal. They then share that data in a common database. And then there's an algorithm running in the database, which then computes the estimate of the unknown position and unknown transmit time of the transmitters. So this is a fully asynchronous system. The receivers have no knowledge of when the transmitters might actually be sending out their information, but they can measure the arrival time using some fun signal processing, which I can talk more about later or offline. But suffice to say, we run something called a match filter detector, and that has to run all the time fast at really, really low power. So therein lies the really fun and challenging embedded hardware and software engineering challenge. We're trying to build a system with receivers that can be as low cost as possible, which means they need to have relatively small batteries, relatively small solar panels to keep those batteries topped up, and therefore relatively power efficient computation resources at each of the receivers that are running this real-time signal processing algorithm all the time, so they can be continuously listening for the unknown event when it may come in. The other tricky bit is that these transmitters are small, and so they're not sending out a lot of power. So you can't just listen for just the amplitude of the transmitter. You have to be running this match filter detector all the time so that you can then pick up the signal. Otherwise, you don't have any knowledge of the signal. So I'm happy to elaborate on that later, but for now, I think I'll leave the explanation at that level. So as I said, I've developed a system a while ago. Here's one example of it working over in the Netherlands in a farming area. There's a couple of birds that are being tracked. So there are the animated dots. And then if you kind of see, there are some numbered dots here. The numbered dots are the locations of a couple of different receivers that I put out over there. And we've since used this in other areas. This is a mud flat that's down in Mauritania. And we're tracking animals on that mud flat. So we published papers on this. I think one of the remarkable things about this approach is that you get so much data. So in this study, we got 43 million position fixes from 46 birds over 5 weeks. So we have so much position data that we can literally just bin up a geographic distribution into, in this case, I think I used 25-meter square bins, and then just counted the number of position hits in each of those bins, and then just used a color, color heat map to indicate how many position fixes happen to coincide with a particular bin. So what this shows is that there are some areas in this resource that are really popular with these birds because they're moving around, and in this case, they're going after some food resources there, these little tiny mollusks that they go for. So there's no other tracking technology that would allow this level of information, this density of information from very small birds. So it's really exciting. I think it could really be a game changer in allowing people to learn about the way that animals use space. You know, that's what kind of motivates me to work on this stuff. These are potentially really, really small tags. So here's some examples of a tag that I built years ago, and we patented it and then commercialized it. So I spun it out to a small company, and this is now something that's called the life tag, sold by this company, Cell Track Technology. What's different about this tag is that it's fully software defined. So you don't have to, you know, change what crystal you're going to use in order to set the ID of the tag, which is the common way of making tags, similar to the ones that I showed you early on in those black and white pictures. It also has a solar cell. This is actually a triple layer gallium arsenide solar cell, similar to what's used out in space. It's a high efficiency cell, so it's about 30% efficient, which is nice. And I just cut it down so it fit on this little tiny tag. And all the tag does is just accumulate solar energy into a capacitor until there's enough energy stored. Then it turns on and does its thing, burning through that energy, and then goes back to sleep again and waits for more energy to come in. So this kind of approach, you know, would allow potentially unlimited, really, really lightweight tags with the kind of tracking system I was just describing. So, you know, I think that the way that this could be used is not just in tracking animals, but tracking everything, you know, so all different sort of layers of the food web, including, you know, like trash items where humans interact with animals or vice versa. And then there are potential other applications which we could maybe talk about. I think the real inspiration is to try to outfit key areas. This is a terrestrial system for now, and so it's not going to be global, but it could be regional. And so there are all these different regions around the United States and around the world that are really important as, for example, stopover spots for migratory birds, or, you know, permanent habitat for terrestrial animals. And it'd be wonderful if we could set up these wireless tracking hotspots in these areas. And so once you've installed the receivers, might take 20 or 50 receivers to cover an area. But once you've installed those receivers, then all you have to do to track an animal is to buy one of these little tiny tags, which are going to be, you know, maybe 10 or 20 bucks in total, stick it on the animal, and then you're up and ready to go. So I think that the idea is, well, one of the taglines I've been joking about is this big data for small organisms, kind of going back to that plot that showed you the heat map with all those different position plots. So anyway, that's 18 minutes of me yakking about position tracking. Let me show you the kinds of things that I'm looking for help with. So this is an ad that I put together for this particular project. And, you know, I think that the involvement from students could come at many different levels. I've been focusing primarily on paid hourly or on research appointments, research assistantships, depending on where the person is in their program, what their goals are, how much time they have. What I'm really looking for is folks who are really well versed already in embedded Linux. It's going to require a really rapid ramp up. And so I think if you don't have a lot of embedded Linux experience already, this probably isn't the project for you, because it's very much about getting that system up and running, you know, like yesterday. I can teach the signal processing stuff, but I don't think I can teach all of the stuff all at once. Certainly, along with the embedded Linux is an expectation of really solid background in C, C++, and also Python. And do I have Matlab in here? Experience in Python and Matlab are useful. One or the other is fine. I think both as high-level scripting languages can more or less be interchangeable. The reason I think that MATLAB's a useful thing is that it's got a lot of built-in tools for doing signal processing work. And we like to prototype code in MATLAB and then port it to C++. And that allows us to verify that the results we're getting are consistent. You know, there's no coding error, I guess, that's occurred when we made the translation to the low-level embedded system. So there's definitely some signal processing involved. So if anybody has prior experience in signal processing, that's great. My guess is that for a CS audience, maybe folks will have less of that than if I were talking to an EE audience, and that's okay. I can fill in some gaps there as necessary. So I think in terms of the hierarchy of prior skills, a lot of experience with embedded Linux is probably the most important thing for starters. And by that I mean, the ability to get a headless system up and running. Also interactions with, I don't have it in here, but interactions with GPU processing. So if anybody has experience with CUDA or similar kinds of GPU computation tools, that's how we're going to make the signal processing run fast and efficiently on these relatively small machines. By the way, the machine that I'm using right now is in the Jetson family from NVIDIA, because it's got a nice combination of CPU coprocessors and then GPU coprocessors, we'll say. So any prior familiar with the Jetson will make you feel a little bit more at home in this project. It's helpful if you've had some experience with device drivers and how they interact in Linux, though not essential. I'm mostly using some existing device drivers for one of the peripheral modules that pulls in data from the antennas. We use this thing called this SDR, which is a software-defined radio. And so the nice thing about what's happened in the last 20 years is that all of that radio frequency engineering that I had to do from bits and pieces is now encapsulated into things you can just buy off the shelf and plug in via USB 2 or 3 port into a general purpose computer, and voila, you have a radio. But still knowing how to talk to it, how to access it, how to use the drivers that come with that radio, that's all a key part of kind of gluing this system together. All right, there must be questions. Any questions about what I said so far? You need not raise your hand, just jump in.
Okay, I'm not sure if I have experience in embedded Linux yet, but I have done work in Raspberry Pi, something like that. Is that what is considered embedded Linux, something like that?
Possibly. So tell me more about what was the operating environment that you were working with? Were you using the Raspberry system and all that?
It was more like an IoT system designed for my senior project. I used a Raspberry Pi connected with a webcam, and once it was a sensor type of stuff that was like taking pictures periodically and then saving it to the cloud and doing some image fusion stuff for detecting a gas system, something like that.
Mm-hmm. Well, I think maybe you and I should chat about that individually, and I can ask you some other questions to see whether what you've done would map to this.
Okay.
Yeah. Let's see. Other questions about this project or about some of the goals or some of the tasks?
I have another question about, I see there is a PCB design. So for this project, do we have to come up with our, a more like a schematic design that could be printed on to a print circuit, something like that?
Possibly. It's there is a component of this work that will require PCB design. I have someone currently who is pretty good at that, and so it's not the key capability that I'm looking for in some new folks, but it would certainly be something we might use. Yeah.
Yeah. Can I continue with another question before another person?
Any other questions there? Anyone else want to jump in? Yeah, was there a hand up somewhere?
Sean, you can ask.
Hello.
Hello.
Yeah. So my question is like, when does the tag gets to know to send the position coordinate, or is it being pulled from the receiver side? I mean, like the antennas which you have set up here. So the antenna gives some kind of a command to like get the position, or the tag has some kind of set of intervals to send the data back. I wanted to know how battery optimization has been happening by, like, when do you find exactly that this coordinate has to be sent back to our system?
Yeah. So in fact, the tag does not ever know where it is. The tag does not have a GPS on it. The tag has no knowledge of where it is. All the tag does is send out a special coded signal that allows nearby receivers to receive that signal. And it's the job of the nearby receivers to then measure very precisely, to within about 30 nanoseconds, to measure very precisely the arrival time of that transmission from the tag. So multiple receivers at different locations make that measurement of the arrival time. And with their knowledge of where they are, we can then compute an estimate for where the tag must have been based on these different arrival times at different physical locations.
So tag continuously okay. So but when does the tag sense that the frequency wave to the receiver?
I didn't catch the
Like,
last
is
part of
there
it.
every some set of intervals or something like that for tracking this movement?
Sorry, it's just a little bit broken up. I didn't catch the last part. Could you repeat that more slowly, please?
I wanted to know the interval rate at which the tag would send the receiving the signal to the receiver.
The interval. So in general, the interval is undetermined. So it can be a regular interval. It could be like once every second or once every 2 seconds, or it could be very infrequent. For example, if the tag is acquiring energy from a solar cell, if you're in a variable light condition, the tag might only get enough energy to transmit every 1 or 2 or 5 minutes. And so then it will send out the signal. And the signals are very brief, by the way. The signals are only about 4 to 5 milliseconds long, and then the tag turns off. So the tags are fully asynchronous to the receiving network.
Thank you.
Yep. The one caveat that I haven't really mentioned is that the receivers, therefore, need to take care to know exactly what time it is in a global time base, because the receivers are at different locations. They all have to have the same time base. And so we work pretty hard in this, and I left out that detail, but it's definitely part of the project. We work pretty hard to try to make that time base accurate and consistent across all the receivers, because that's what allows the system to work.
Thank you. And also, sorry, my last question. So since you said there are a lot of receivers, is there some kind of consensus algorithm happening between this receiver to figure out what distance, the right distance captured?
Yeah, so it's not explicitly a consensus algorithm. If you think about what we have a bunch of measurements of arrival time at different locations. And so we're trying to solve for a variety of unknowns. We're trying to solve for the transmit time, and then X position, Y position, and then possibly Z position if we're trying to make a 3-dimensional position fix. So in general, we're trying to find 4 unknowns. And so, if you need to find 4 unknowns, you need to have 4 equations to solve. And so to have 4 equations to solve, you have to have 4 measurements. So you have to have 4 receivers that receive the same transmission at different locations in order to compute a position estimate at minimum. Once you have more than 4 receivers, then you have an overdetermined system of equations. And so the most straightforward way to solve that is with a least squares approach, just like you would if you were trying to solve any linear system. This is not a linear system, it's a nonlinear system. And so we use a nonlinear approximation approach to solving these systems of equations. But in a similar way, we use a least squares fit type.
Thank you.
Yep.
We have Amir.
You said that the receivers need to have they need to be small or have like a small battery or something. Why the receiver? Because the bird or anything, they don't need to carry it.
I like your intuition. Yeah, you're right. I mean, the whole point of this is to offload all of the energy and computation from the animal, which does not need to know where it is, to the receivers, which can be stationary and pre-installed. However, we want the receivers to be as cheap as we can possibly make them. And so in general, it won't be possible to have power and data at each of the receiver locations. In general, they'll be just out somewhere where it's convenient to put them, and then they'll have to telemeter their received data back to some base station. So they'll have to run from their own batteries and their own solar panels. And so therefore, making them as energy efficient as possible will make the batteries and solar panels as small as possible and therefore reduce the cost. And there's a real motivation to try to make the cost of the receivers as low as possible, because you need a relatively large number of receivers out in the world in order for the system to work. I mentioned before that the range is between 5 and 10 kilometers. That very much depends on what the terrain is like. These radio signals cannot pass through the ground. And so if you have a very mountainous area like around here, you'd want to have a more dense grid of receivers than one receiver every 5 kilometers, for example. So the goal is to make them as low cost as possible so we can make them ubiquitous.
Thank you.
Yep.
Yeah, I have another question. Is it possible for us to use the passive tag on the animal itself? Like
Yes.
I've seen applications on earthquake detection where they use base stations, and it's more like a triangulation to find the epicenter of the earthquake. I'm not sure if that's possible if we do that with a passive tag. So what we do is each receiving center, like it will emit like a radar, and then something might be reflected back to each station with a different response time, something like that. And
Yep. There's a wonderful, relatively old paper now at this point, I don't know, 15, 20 years old, something like that, that used what's called a harmonic radar. And so they put relatively powerful, I think it was a 1 to 5 kilowatt sort of emission power radar on the back of a truck. And that radar had a nice antenna, sort of classic parabolic dish antenna. So it could create a focused radar beam, and they would sweep that through an area. And then they put these little antennas on the backs of honeybees. And the antennas were effectively 2 very short lengths of wire with a diode in the middle. And what happened is when the radar was incident on the diode rectified the incoming sinusoid to double its frequency. So if you think about a sinusoid, it goes up and down. Now, if you just rectify that, meaning you just take all of the negative parts and flip them up, you kind of have a doubling in frequency of your signal. And so you can then receive that doubled frequency back at the radar receiver. The downside of that approach is that it requires this truck-based system, and they were only able to get, I think, up to about 500 meters of range from this system, because it required a lot of power at the receiver. I'm sorry, I was conflating it as the receiver. The tag requires a relatively high amount of incident power in order to turn on that diode rectifier. Below a certain threshold, that diode is not activated, and therefore the rectification and doubling of the frequency that's returned back doesn't occur. So, and that story still holds true for all of these passive approaches. You may have heard of RFID, for example, and the longest range RFID systems can operate, people claim, 5 to 15 meters. That's in some cases possible, in some cases a bit optimistic, and there are a lot of caveats that have to do with the size of the receive antenna and whether or not the receive antenna, and when I say receive antenna, I'm talking about the reception on the tag that is being activated by the source of emissions from you with the reader. So that receive antenna, sometimes people put a small battery on that receive antenna to make it more sensitive to being turned on. So anyway, for all those reasons, I'm doubtful that these so-called passive systems or harmonic radar-like systems will be the way to solve the kind of regional scale tracking that I'm talking about. I'm envisioning putting out receivers on a grid and having an area, sort of the size of all of Boulder and the Front Range covered, for example, with a regional tracking system for animals and assets, bikes, etc.
Nice. Thank you.
Great question. Other questions?
Yeah, I have a question about the data aspect. There's a main goal is making the chip receiver and making the receiver as much as less. And if then they have some problem to the data to get the data. Some case the weather or obstacle or something, any problem maybe happen. So how to adjust the time series data to the track data? Maybe something miss in the whole data. So they need to assemble and adjust to do the result. So how to do that?
Well, it certainly does happen that not all of the necessary receivers will actually detect a transmission at one time. So, as I said, you need to have 4 at minimum receive the same transmission at the same time. And depending on where the transmitter is, they may not. And so in these cases, there's not much you can do to get a position out of that because you just don't have enough information. You can, as a fallback, you can make, for example, a simple presence absence detection event. So you can say, well, a receiver that's over, down in South Boulder, it picked up a transmission at 1:59 p.m. From tag number 37. So I know that tag number 37 was within the reception range of that. And if 2 receivers pick it up, you can actually differentiate down to a hyperbolic curve using a classic time difference of arrival based approach, which, by the way, we don't use TDOA or time difference of arrival. We use a full time of arrival based approach, which is more accurate. But at the end of the day, what will happen is that there'll be a database that's full of these reception events from all of the individual receivers. And so that database can be queried and different algorithms run across it, depending on the quality of the data that's there in that repository. Great. I'm happy to keep taking questions about this project, or I can show you the other major research theme in the lab if you like, so we can just get a full idea of what we're doing. Why don't I switch to that? Let's see here. Okay. All right. So I should have said this before. My lab's title is the Matter Assembly Computation Lab. And that is meant to reflect the idea that a lot of what we do in the lab is computational design and fabrication. And this is it's admittedly a large topic switch from this radio frequency tracking stuff, but that's how it is. So we're doing in this set of slides, I'll show you about computational design and fabrication of soft robots. So the problem we're trying to solve is that soft robots don't have the performance that we would like them to have. So most of them are based on this canonical so-called NuNet design, and they're fabricated manually via single material casting. We could do better than that. We could use multi-material additive manufacturing to potentially increase the performance of these fingers. So we'd like the fingers, in the ideal case, to be as forceful as a human hand, as compliant as a human hand. Things like dexterity, grasping, that's at a higher level, I think, up the capability stack. I'm really talking about just the mechanism, the mechanics of these things. So conventional soft robots do pretty well. They can conform around an object automatically. They are quite tolerant of uncertainties in the shape of an object that they're trying to grasp because they're soft, so they can kind of wrap around something. So we'd like to maintain that soft, compliant, conformal behavior, but to make them stronger, able to lift heavier objects, and lift heavier objects in multiple orientations rather than just a single dominant orientation. So in order to solve that problem, my argument is that it's a design challenge. It's a multi-material design challenge. How do you put what materials, different materials where in the design of a finger so that you can make that finger both compliant in the right directions and also stiff in other directions? And one way to do that is just to have really smart people think about it for a long time and do a lot of experiments and try to figure things out. That's basically what we've been doing, right, up until today, sort of the status quo, and it's gotten us to where we are today, but there's still work to be done. And so my argument is that another way of solving the problem is to have the machine do the design and fabrication. So in order to get there, we need to have the way some mechanism for automatically fabricating these things. We need to have a way of automatically defining what the shapes should be, and then some way of translating from desired shapes to actually physically printable designs. And if anybody has ever 3D printed something, you may have had the experience of some design that you came up with. Most of it worked, but parts of it actually didn't 3D print because of limitations in the fabrication process. And so this is what I'm talking about in point number 3, is some mechanism for understanding what the fabrication limitations of these 3D printing approaches are, and then incorporating that into the design. So the goal is to evolve or design soft robots, and this is an allusion back to a video that I made some number of years ago that I guess I'll just skip that for now. So let me just give you a brief overview of some of the fabrication stuff that we do. This is a 4-material 3D printer that we developed. Multi-material 3D printers are not totally unique in the world, but what is unique about this printer is that it's designed to print not just with filaments, but with basically anything. So it's got syringes. We could print anything from water to ABS. And the idea is to be able to fabricate all of the components that are necessary in a hand or a finger or some other robot structure all at once, rather than having a bunch of sequential processes that need to be manually executed by somebody. Here's an example of an actuator. And this is a conventional so-called new-net style actuator. And what I'm showing you on the right-hand side are finite element models of that actuator when it is under load. So load based on some blocked force here where it's pushing against something, and also pneumatic load from being inflated. And so this one is our optimized version of this one by using computational design tools in order to get a design that better manages the stresses. So the takeaway in these images is that if you see these reds here, all this red and white, those are areas of very high stress in the material. And if the material is capable of bearing that stress, then it's not really a huge problem, except for the fact that whenever you're creating stresses in an elastic material, you are basically storing energy in that material, which then gets lost. So you're doing all this work on the material to stretch it out using this compressed gas that you're pushing into it. And then you're pushing on something. And then as soon as you release the pressure to cycle the actuator, all that compressed gas and all of that stored strain is lost. So it's a less efficient actuator than an actuator that doesn't store as much stress in the body of the actuator. And so this design is storing much less stress in the body of the actuator. And so we started in the lab to try to compare all these different actuators along different metrics that we think are valuable. So we have a figure of merit that's talking about how compliant or deformable an actuator is. So this is the idea that you want soft robots to be soft. And then another one that's somewhat in tension with that first one is that you want them to be strong. So you want something that's really compliant, but you also want to be able to push really hard. So those are kind of different or conflicting objectives. And yet we'd like the same actuator to be able to do both those things at the same time. So we're plotting the performance of a lot of different actuators here on this chart to compare. And you know, naturally, our design comes in somewhere at the Pareto front of these things. And we can talk about what the Pareto front is later. So anyway, we're comparing actuators. This is the design of the actuator. It has, in this case, it actually has a printed in sensing element. It's a resistive strain element that allows us to measure the strain. And here we're actually looking at this actuator inflating, and then there's a strain signal that allows us to tell how much it's deflecting. We can use that as a proxy for how hard it's pushing. I'm going to skip past some of these things just in the interest of time. So the upshot is we can 3D print these actuators that are multi-material, that are soft, but also have embedded strain sensing built in. This is a section that's about automatically generating the shapes for these objects. So this is an approach that we've developed that creates computational networks. In other words, they just create functions. So I'm going to show you some networks here, which are, you know, there's some inputs that correspond to, in this case, the theta input. So in a cylindrical coordinate system, you know, you've got theta and r and z, right? So those are the inputs that describe your space. And then the function takes those inputs and does something with them, and then creates a scalar field in that space. If you then take a level set through that scalar field, in other words, you take all the locations in that space that your function defined as having some value, and you say, give me all the spaces, sorry, all the locations in that space where the output of the function was 0. If you do that, you get this surface, for example. Right? So if you, here's a function, for example, this particular function that created this surface. And if you then inflate this thing with pressure, which we can do using a simulation engine that we've developed, then you can see in kind of real time how the thing you've just developed using this network, how that actual device might operate, how it might function. Hopefully it's not terribly confusing to see this network. I mean, this network is composed of a bunch of primitive operations. So there's the identity, which is just that whatever comes into it goes back out of it with a scale. There's a sinusoid, so all the red ones are sinusoids. So anything that gets passed into it, you pass the sine output from it. There's a fourth power. So in this case, something goes into it, that's x to the fourth out of it. So it's a graphical depiction of a function that you can just write out on one line that takes as input the theta, the r, and the z of a cylindrical coordinate space. So there's a one-to-one mapping between a function that you can write down on a line and between this graphical depiction of a function. So why do we use the graphical depiction of the function? It's more intuitive to edit that thing when you have this graphical user interface, which allows you to drop individual activation functions, these little things here, and then connect them with connector lines, etc. So we can create these functions, and then we pass the input of the functions into the functions. We pass the position in three-dimensional space, and out of the function for each of those locations in three-dimensional space, we get a number. And so you do that over and over again for all the different locations in three-dimensional space. And then you draw a curve through all of the numbers that are equal to something. So in this case, all the numbers that are equal to 0, you draw a curve through them. We call that curve a level set. And that defines the outer surface of the object that we're trying to represent. So that may seem really convoluted. The question is, you know, why would you design something this way rather than using interactive CAD? And the answer is that I would argue it's actually much faster to manipulate objects like this than it is to design something like this in interactive CAD. Now, you could probably go in and make one of these in interactive CAD once, but then when you need to modify it, when you need to make tweaks to it to change the performance, that's when the power of this method really shines through, because we can actually optimize over the space of these networks. And I've got a paper that was the next one that I won't show you today, but if anybody wants to talk about it, I can show you, where we actually use an optimization algorithm that then modifies the network in order to get an output that we want from the mechanical behavior based on a simulation, based on a finite element simulation. And here are a few examples of the many different types of fingers that you can generate using this approach and using very, very similar networks, even though the fingers themselves are qualitatively very different from each other. So the point is that by using an approach like this, you can get much more flexibility in the kinds of objects that you can design. And this approach of level sets also makes it really easy to compose different things together. So here's a notional 6-legged soft robot that was made just by composing 6 of these original fingers together and then inflating them. So the last thing that we're doing, and I don't have enough time to really go through this, but the last thing we're doing is developing a system that's kind of based on a computer graphics-like view of the world that is a compiler for geometries. It's a compiler for multi-material geometries inspired by something called OpenSCAD. So if anybody's ever used OpenSCAD and you want to learn more about this, I'll have plenty to talk about. But the goal is to be able to enable people to write functions similar to the ones I was describing previously and compile them into volumetric multi-material descriptions of geometries. So let me just stop there and open for more questions. I'll leave it on this one. I can also, another way of concluding is to say that if there are folks who have particular expertise in computer graphics, you might want to have a chat with me. If there are folks who have particular expertise in conformable or deformable simulations, if you have experience with finite element methods or things that are related to that, we have lots of need in the lab for people who want to work on efficient ways of simulating multi-material, highly deformable objects for these kinds of applications. And let me see, I can show you another posting that I put out. Okay, so can you see this this Word doc? Okay, yeah. So yeah, if there are folks who want to look at numerical solutions to continuum mechanics problems, there's obvious overlap between this and a kind of more ME way of looking at the world, but increasingly folks in CS are really, really involved in these kinds of problems, especially at the frontiers of really high performance. And so if you're interested in these kinds of things, I'd love to talk with you more. Here are some possible prerequisites for classes that you might have taken or might want to take if you're interested in this kind of area. And here are some possible recommendations for software packages to know about. In particular, experience with Abacus or ANSYS is really valuable as a basic foundation in doing numerical modeling of continuum mechanics. All right. Questions?
If not.
Well, I should have put my email address here, but I think do you all have my email address?
I can share it. Yeah, it's in our pre-research advising
Right.
session sheet that I've shared with the students. So
Yeah, it's just MacCurdy, my last name. I don't know why there's a space here. There's no space in my last name, but just MacCurdy@colorado.edu. So write to me. I love to talk about this stuff. Happy to chat with anybody who's interested. So please don't hesitate if you're interested in these kinds of topics.
okay, with that, thank you so much, Rob, for your time.
Yeah, thank you all. Thanks for your attention.
We'll be posting the video as well for students who couldn't attend today. So we really appreciate it. Thanks a lot.
Great. Thanks. Take care, everybody.
Take care.